Test, test. Perfect. Hm? Ja, das ist meins. Yeah, perfect.
So, welcome everyone back from the cafe break. And the very first talk will be done by Xavier about circuit minimization. Please go ahead.
Thanks for the introduction and hello everyone. In the following, I will talk about our tool eSlim, which is a tool for reducing the size of Boolean circuits. And this was joint work with Friedrich and with Stefan. Okay, so this tool mainly deals with two problems, namely exact synthesis and circuit minimization. So let me start with a brief recap of these two problems. So first of all, in exact synthesis, we are given a Boolean function. So here, for example, given as a truth table, and we want to compute a minimum size circuit representing this Boolean function. Now, computing such minimum size circuits is a hard task. And so it was shown that for a given truth table, it's NP complete to find a minimum size circuit. And also in practice, we cannot expect to find a minimum size circuit with much more than around 10 gates with 2 inputs. But of course, we also want to have smaller representations for larger circuits. And this is the reason why we consider another problem, namely circuit minimization. So here the task is that we already are given a circuit, and we want to find another circuit which has fewer gates, but which still computes the same function as the original circuit. But now the resulting circuit is no longer guaranteed to be of minimum size, but of course, we can now apply this also to larger circuits. Now in our tool, we combine these two things. So this means we want to reduce the size of a circuit by considering sub-circuits and replacing them by optimum size replacement circuits. So let's have a look on this example. So you can see here a circuit where here we want to replace this marked sub-circuit. Now you can easily see that in this sub-circuit, we compute the conjunction of 3 inputs. So we could now think about what's the optimum size circuit doing this, using gates with 2 inputs. So we can realize this circuit by the following circuit. So you can see that obviously this sub-circuit computes the same function as the original sub-circuit, but we have fewer gates. And so if we replace the original circuit by this one, we get, so the overall circuit still computes the same function, but we could reduce the size. But now for computing this circuit, we only considered the sub-circuit. So we completely ignored everything outside of the sub-circuit. And this is not necessarily the best way. So for example, let's have a look on this input I2 of the sub-circuit. So you can see that if this input is true, then both B and C need to be true, of course. And thus, it's not possible that I2 is true and I3 is false. So there may be some input combinations which can never arise. And for such input combinations which can never arise, the subcircuit can show an arbitrary behavior and it doesn't change the function computed by the entire circuit. Yeah, such combinations are also called don't care because they don't have an influence on the entire circuit. And now we can make use of these don't cares. So let's have a look on this circuit. So you can see that if this gate yields true, then also this input needs to be true, and thus the overall result is true. If on the other hand it's false, then of course it's also false. And this means we don't need the second gate. And thus we can replace the original subcircuit by this one. Now obviously the two subcircuits are no longer equivalent, but if you look at the entire circuits, they still compute the same function, and we could reduce one more gate. Okay, so now to compute these circuits, these minimum size circuits, we want to make use of SAT solvers. And this means that our approach falls to this SAT-based local improvement method or SLIM paradigm, which was used for various domains to improve improvements. Okay, so how do we proceed? So to compute the replacement circuit, we proceed in two steps. First of all, we compute a representation of the subcircuit, and in a second step, we compute the circuit realizing this representation. And to represent the subcircuit, we make use of Boolean relations. So Boolean relations are just functions that map assignments of the inputs of the subcircuit to some set of permissible output assignments. So this means that for every circuit that yields for every input assignment, one of the permitted output assignments, we want that this circuit can be used to replace the original subcircuit. Okay, more formally, a relation can look like this, such a function. So let's illustrate this with an example. So here we again have a don't care because again we see if this input is true, then both B and C are true, and thus this input cannot be false. So how would a relation for this subcircuit look like? So first of all, you can see that if all of the inputs of the subcircuit are false, then of course the output must be false because if we would change the output here, then obviously we would change the function computed by the entire circuit. So here we have just here the output not. And if you look here at this line, you can see here's the second input is true and the third one is false. This is exactly such a don't care combination, so an input that cannot arise. And thus, it doesn't matter how the output is assigned. And this is represented by this line. Okay, so how do we get the relation? So the idea looks as follows. So we start with the original circuit. We copy this circuit. And then in the copy, we cut out the selected subcircuit. And now we introduce for each output of the subcircuit a new input. So this, in total, we have two sets of inputs. So first of all, the original inputs, and secondly, these new inputs. And then we ask, can we find some assignment for these two sets of inputs such that the two circuits differ? If this is the case, we found some output behavior of for a replacement which would cause some problem. Yeah, and if we find such an assignment, we can also get an assignment for the subcircuit from the assignment I because this is directly entailed by the input assignment of the entire circuit. So we can get this assignment K. So this means we can find a pair of input and output assignments of the subcircuit, which would cause a problem. So this means a subcircuit with this behavior would change the function computed by the entire circuit. Okay, now we want to compute all these pairs. And for this purpose, we make use of incremental SAT solving. So this means we make use of a similar idea as presented before. So this Mitre construction. So with this, so we have clausal representations of the two circuits. And then, we ask if one of the outputs differs. This allows us to check to find assignments K and J. And if we find such an assignment, we just add new clauses which rule out these pair of assignments for subsequent iterations. And then we just repeat the search for new satisfying assignments until we can find no further assignments. In this case, we found all these pairs. Now, by complementing this set of pairs, we then get the evaluation, because only the input-output behaviors in this pair would change the function. So every pair which is not contained is okay. Okay, so now we have the relation, but how do we get the circuit? So here we adapt some SAT encoding for exact synthesis. And this encoding does not directly allow to compute the minimum size circuit. Instead, it allows to check whether there's a circuit of a given size which represents this relation. So we have here this size K. And now this encoding basically looks as follows. So we have for each gate a set of variables which describes the function at the gate, variables which describe the inputs of the gates, and variables which describe which output of the subcircuit is represented by which gate. This is just a set of variables. So I don't want to go into too much details for this encoding because just there's not enough time. But we have, this is set here. You can imagine if we have, for example, 3 gates, then for each gate we represent the function by a truth table, and for each line in the truth table we have one variable, and this variables would be contained in the set S.
Fine.
Yeah, because so usually call S the original subcircuit and S prime is the replacement circuit, and this replacement circuit is just represented by this set of variables. So yeah, it's not the best way to use this prime, you're right. So, but usually we make this distinction. Original subcircuit is S and the new one is S prime. And yeah, as this set of variables describes the subcircuit, we have this correspondence between variables and subcircuit. Okay, and then to check all the different sizes, we make use of incremental SAT. Again, make use of incremental SAT solving. So this means we add for each gate some variable which allows to deactivate the gate. And then if the SAT check succeeds, we can turn off this gate, so to say, and we check for a K-1. And this we repeat until the encoding gets unsatisfiable. And here, last but not least, for each pair in the computed pair, so for each pair which we computed before, we add this clause. So this means if we have an input assignment J, then we have to ensure that we have not K. And this means that, yeah, we get an output behavior which is not problematic. So an output behavior which would not change the function computed by the entire circuit. Okay, so now the overall algorithm looks like this. So we won't talk about this computation of the subcircuit just because of the lack of time. So we pick a random root gate. So we then expand this root gate into a subcircuit. For this subcircuit, we compute the relation. And then we make use of this SAT encoding in order to get the replacement circuit. So as I said, here we need some size. And for the size, we use the original size. And then we just decrement this size until the encoding gets unsatisfiable. And this means that the last size, the last value for K, for which the encoding was satisfiable, is the minimum size. Yeah, we can then get the actual circuit from the satisfying assignment, and we can use it to replace the original circuit. Okay, you might ask why we start with the original size, because this encoding will always be satisfiable. So the reason is that we want, in case there's no smaller circuit, we still want to change the structure of the whole circuit. And by making this SAT check, we find some satisfying assignment, and this usually corresponds to another circuit. So most often we can change the structure of the circuit, which helps to improve the circuit. Yeah. Okay, so now what does our tool then do? So, so we start with some input circuit, then we apply our method with some given local timeouts. Afterwards, we apply the synthesis and minimization tool ABC, which also Armin mentioned before, with some much smaller timeout as an in-processing step. And then we repeat this as long as we have time. So we have a local timeout for our method and then a global timeout for the combination of the two steps. In the end, we then get a circuit which computes the same function as the given one, but which has fewer gates. We can also apply our method in parallel. For this purpose, we split the given circuit into several windows. So windows are just larger subcircuits. And here we apply our method to all the windows in parallel. Then we combine the windows again. And then we again apply ABC for in-processing. And then we repeat this as long as we have time. In the end, we get again a circuit which has fewer gates and which computes the same function as the original one. Okay, now a few words to the tool. So it's freely available at GitHub under an MIT license. It's mainly implemented in Python with some parts in C++. It supports different numbers of inputs of the gates. So not only binary gates, but also gates with more inputs. It also supports certain specific types of gates circuits, for example, ARGs. We only allow specific functions for each gate. And as a SAT solver, we used Cadical. Now, for a few words about some experimental results. So we compared our tool with a previous approach, which was based by QBF encoding and by ABC. So here we use the command deepsyn, which is the state-of-the-art command from ABC for any time optimization of circuits. And we use the instances from the IWS Programming Contest 23. So here the task was to compute small ARGs for given Boolean functions. So here you see the average reduction of gates in percent compared to the initial circuit. Then here we distinguish between we split up the instances in classes according to the number of gates in this initial circuits, and we compare here deepsyn, the old QBF-based approach, and here the SAT-based approach, which I presented now. And you can see that our tool could really solve more, could reduce more gates than the old version of our tool, and it could reduce significantly more gates than deepsyn just alone. While we use deepsyn also as in-processing, so we give the same time for deepsyn here as for whole setup for our tool. So we have the same times here. Okay, so I think I already run out of time. So thank you for your attention, and I hope I can answer any question.
No questions, we have time. Yeah. Okay, we have a question already here, but then after it.
Friends, how do you select the subcircuit? How do we select the subcircuit that is to be minimized?
It's a very simple strategy. I mean, it may look too simple. So we just pick a random gate, and then in some graph search-like manner, we select some gates which make use of this gate, and then with a certain probability, we either add it to the subcircuit or not. And then we just continue this until we have a sufficiently large circuit. I mean, this may sound too easy, but we also applied our other selection strategies, and the randomization really worked better. And I think this corresponds to other applications for SLIM, where also randomization really helped a lot, because this really allows to cover a lot of different structures in this circuit.
It's just one subcircuit that is selected, and it is one subcircuit.
Also, not one. We incrementally select a lot of subcircuits. So we have some time budget, And so we can run our algorithm as long as we want. So if you want to run it for a week, you can run it for a week, and then usually thousands or millions of subcircuits are selected. And if you just wanted to run it for an hour, then of course less subcircuits are selected. But there's not really a limit on the number. So this just depends on the user, how much time he or she wants to spend.
Thank you.
Yeah, can I ask a question? So in this bar chart, so that so what is the number on the instance class? Means what?
This is the number of gates in the original circuit. So we start with some circuit, and then we want to improve the circuit. And here this is, so there were also a circuit with less, with few. But for this, it's not really a problem because this encoding is just related concerning with the subcircuit. So, and it only depends on the number of inputs of the subcircuit.
Okay.
Yeah, so you're getting better circuits, right? Smaller circuits, and then I assume you checked them to be,
Yep.
and were they harder to check?
These circuits were easy because they're just not so big. So we also checked, for example, there's this EPFL benchmark set with 6 LOTs, and for these circuits, it was sometimes very time consuming to check. So for some instances, it took several days to check equivalence. So checking the equivalence took more time than improving them. But for these instances, it was no problem because it was a matter of seconds to check equivalence of these IWS instances.
Okay, then let's thank again the speaker and we can continue. And the next talk will be by, I don't dare to pronounce, but it will be about boosting entailment.
Okay, can you hear me okay?
Yes.
Yeah, okay. Hi everyone, my name is Yogev Shalmon. I'm a grad student at the Open University of Israel, and I also work at Intel as a student. Today I'm going to present you our paper, Entailing Generalization Boost Enumeration, which is a joint work with Dror Fried, Alexander Nadel, and Roberto Sebastiani. So first I want to talk about combinational circuits, which are important in our context. So combinational circuits are a type of digital circuit where the output is solely depends on the input. So given an assignment to the input, we can know the value of the output. And in our context, we only have one output. So the output is connected to the inputs with gates that corresponds to logical operators like AND and OR. And here we have an example of combinational circuit. So we have 3 inputs, A, B, and C, 2 AND gates, N1 and N2. And the output here is equal to the negation of gate N2. So how can we satisfy a combinational circuit? So first, we only consider assignment to the circuit inputs. We do not consider any assignment to the internal gates. Secondly, we need the output to be evaluated to 1. So here on the left, we have an example where the assignment does not satisfy the circuit since the output is evaluated to 0. On the other end, here, we have an example where the assignment satisfies the circuit since the output is evaluated to 1. Also note that assignments can be represented as cubes. Cubes are conjunction of literals. So if I have the assignment A is assigned 1, B1, C0, this is the same as saying A and B and not C. So instead of using assignments with only Boolean values, we can use assignments with don't care values. We can think of a don't care as a new value that can be either 1 or 0. Also, we omit don't care value assignment. So if I have the assignment A is assigned don't care, B don't care, C 0, this is the same as just saying C is assigned 0. So I omit here the variables that are assigned the don't care value. So now we say that assignment satisfies the circuit if propagating the values, including the new don't care values, result in the output to be evaluated to 1. So here we have the new rules for the don't care values. So a negation of don't care is don't care. Don't care and 0 is 0. Don't care and 1 is don't care. And don't care and don't care is don't care. So here we have an example of an assignment that satisfies the circuit when the assignment have don't care values. So here the value of gate N1 is don't care, since don't care and don't care is don't care. The value of gate N2 is 0, since 0 and don't care is 0. And the output is evaluated to 1, since it's the negation of gate N2. So this assignment satisfies the circuit. The problem is that when we want to define what is a solution, satisfaction may not be enough. In the essence, that some solutions may not satisfy the circuit. And now we'll see a short example. So here we have a new circuit, and this circuit this formula represents this circuit. So we have A and not B, or A and B. So this represent the circuit. If we assign A intuitively, it should be a solution. So we don't care about the value of B. Because if A is assigned 1, we have not B or B, which is a tautology, so we don't care about the value of B. So the assignment A is 1, B is don't care is a solution. But now let's see if it satisfies the circuit. So now I assign the assignment to the input value. So A is assigned 1, B is don't care, and now I propagate it to the output. And now we can see the output is evaluated to don't care. It do not evaluated to 1. So this assignment does not satisfy the circuit, even though we know it is a solution. So this is a problem. So we just saw that satisfaction may not be enough when we want to define what is a solution. So instead, we can use another definition. Now, we say that an assignment is a solution if and only if it entails the circuit instead of satisfy it. So an assignment entails the circuit if we take all the don't care values, replace them with any Boolean values, so by replace them with 1 or zeros, and check that all this combination satisfies the circuit. So a little bit more formally, any assignment, any total Boolean assignment that is subsumed by my original solution need to satisfy the circuit. So if, for example, we have the assignment from before, so the assignment A is 1, B is don't care, the assignment where I replace the don't care value with 0, so the assignment A is 1, B is 0 is subsumed by my original solution. So the key observation here is that entailment is stronger than satisfaction. And we can use that observation when we generalize. So generalization is the process of taking an original solution and replacing Boolean values, so replacing 0 or 1s, with don't care values. So we reassign the variables. So we can think of it as intuitively obtaining more solutions, because if I have more don't care values, I cover more total Boolean solutions. So here we have an example of generalization. So here we have our initial solution, A0, B0, C0. And here we have a truth table. So now we only have one solution. And now I want to generalize it by reassigning B and C. So when I assign B and C the don't care value, I generalize it to the assignment A and 0. A 0, B and C are don't care. So this is a solution. And we can see now that we cover 4 solutions. And what's important here is that we need to ensure that when we replace Boolean values with don't care, we are still a valid solution. So this is how this is important because we need to define what is a solution. And then we can use the entailment definition instead of the satisfaction definition. So our key observation in our paper is that when we generalize a solution, we can categorize it into the following. So the most restrictive one, the gauge generalization, which we did not mention, we have more details about it in the paper, require that the generalized solution satisfies the circuit and the values of the internal gate are not equal to the don't care value. Then we have the satisfying generalization that require that the generalized solution satisfies the circuit. So taking the assignment with the don't care values, propagating to the output results the output to be evaluated to 1. Then we have the least restrictive one, so the strongest one, the entailing generalization that require that the generalized solution entail the circuit. So if we take the assignment, replace any don't care values with Boolean values, result in all the combination to satisfy the circuit. So until now we talked about entailing generalization in theory. Now we want to put it into practice. So we took a non-generalization technique that use answered core extraction. So let's briefly overview what is answered core extraction. So we know that a SAT solver given a CNF formula can decide if the formula is satisfiable or not. In addition, on top of that, SAT solver can receive a cube of assumption. So for example, A and B and not C. And then the solver can decide if this formula under those assumptions is satisfiable or not. If it's satisfiable, then it will return us a solution where the assumption hold. If it is not satisfiable, it can return us an unsatisfiable core. So an unsatisfiable core is a cube which is the same or smaller than my original cube of assumption, such that the formula under this cube is unsatisfiable. And now let's see how we can use that to generalize. So first, we need to generate the dual circuit of our original plain circuit. So the dual circuit is the same circuit, but now we evaluated the output to be 0 instead of 1. So now every solution in my original circuit is guaranteed to not be a solution in the dual circuit. Since I know a solution in my original circuit, the output is evaluated to 1 and not to 0. After I generate the dual circuit, I convert it to CNF, and now I have the dual CNF of my original circuit. Now, every time we have a solution in our original circuit, we can do the following. We take our dual CNF formula and our current solution as a cube of assumption. So if I have the assignment A is 1, B0, C0, I take the cube A and B and not C. And now I ask a SAT solver, is it satisfiable? Note that at this point, the solver must return unsat, since by definition, this is a solution to my plain original circuit. So of course, it is not a solution to the dual circuit. After the solver return unsat, we can get the unsat core. So a possible core here is, for example, A and B, which equivalent to A is 1, B is 1. And the unsat core here is guaranteed to be a solution to our plain circuit. So our application is the all SAT enumeration problem. So given a circuit, we want to find all the solution to the. So here we have the same circuit from before, and here we have the truth table of the circuit, and we want to cover all these solutions. So for example, we can use this free solution to cover this entire set. Note that each solution here is covered by some solution in this set. So if, for example, I have the solution A0, this covers these 4 solutions. So using the observation about intelligent generalization, we utilize it to boost our enumeration application. So last year, we had a paper about all SAT for conventional circuits, and we also had a tool that can solve the problem called HOL. So HOL is based on blocking algorithm that are that are based on generalization. So if we can generalize better, the algorithm will be more efficient. So we developed new algorithm that utilize intelligent generalization instead of satisfying generalization, and we integrate them into our tool. So our main result is that the new algorithm boosts the performance and the quality of our tool. So for our experiment, we compared our new algorithm against our previous algorithm of HOL, and we compared ourselves with Daoliza, which is a projected model counting tool that can also do all SAT enumeration. In total, we have 140 benchmarks, and we evaluated 3 criteria: the number of solved instances when the timeout was 1 hour, the part 2 score in terms of runtime, so the runtime if the instance was solved, and a penalty, so double the timeout if it was not solved, and quality. The quality here represents how compactly did the algorithm manage to cover all the solutions. So if one algorithm produces 3 solutions that cover the entire set of all solutions of the circuit, and another algorithm produces 10 solutions that cover the entire set of all solutions, that I would prefer the algorithm that produces the least amount of solutions. So quality is a number between 0 and 1 that represent how good the algorithm managed to compactly represent the solutions. So this is our main result table, and we will mainly focus on the highlighted line. So here we have Daoliza in its 2 modes, our 3 previous algorithms of HOL, tail, duty, and Mars, and our new algorithms, ROC, core, and karma. So tail is our previous algorithm that uses satisfying generalization, and core is a new algorithm that uses intelligent generalization. We can see that core outperforms tail. So intelligent generalization, instead of satisfying generalization, managed to boost the number of solved instances and the quality, and also the part to score in terms of runtime. Now let's take a look about ROC. So ROC is the combination of tail and core. So actually, core is taking generalization of tail, and on top of that, running generalization of core. So it's the combination of satisfying and intelligent generalization. So even though the part to score and the number of solved instances here are pretty much the same, in terms of quality, ROC outperform core. So when we combine satisfying and intelligent generalization, we manage to get the best result. So a little bit of dive in. So here we have plots of core versus tail and ROC versus tail in terms of quality. So here are instances where tail outperform core in terms of quality. So this, for example, tail managed to get 1 of 1 in terms of quality, and core only managed to get, let's say, 0.42. And when we upgraded core to ROC, so we combine tail and core, all the instances in terms of quality are better than tail. So this is a huge boost in terms of quality. So to sum things up, we introduced the generalization hierarchy where the intelligent generalization is stronger than satisfying generalization. And using that observation, we managed to improve the state of the art in our enumeration application by combining satisfying and intelligent generalization. That's it. Thank you.
We have time for maximum 2 questions.
Thank you for the talk.
Yeah.
You mentioned about static timing analysis,
Yeah.
and can you explain more? Usually, STA, the timing analysis, does not require the function analysis. It's just purely structured, right?
Yeah, I mean, we have more details about it in our previous paper from last year. I didn't have any time to go into depth. I can't really elaborate due to some IP consideration at Intel, but in short, we have some circuit that can be also sequential or something. And on top of this circuit, we construct a new combinational circuit that represents all the path or assignments we want to verify in our original circuit. So by iterating all the solution in this combinational circuit, we actually iterating all the problems we want to verify in the original circuit. So this is some, I mean, in short, but yeah, I hope it it answer your questions.
Okay, we can have more discussion.
Okay.
Later. Yeah, thank you.
Your motivating problem was all SAT.
Mhm.
But no one wakes up in the morning and says, I need to solve all SAT today. They have another problem trying to solve, and all SAT is an instrument for solving some other problem. So what is the underlying problem? And
Yeah.
does your approach really would solve properly the underlying, the real problem, which is not all SAT. All SAT is an instrument.
Yeah, so the actual problem is the static timing analysis problem. So I didn't really have much time to go into depth of our industrial motivation, but given a circuit, you want to verify that the timing of the circuit, so the timing that the propagation from the input to the output, hold under some constraints. So it's not too fast or not too slow. So to verify it, you can either go over all the combination of the input assignments, which can be very large, or you can iterate some partial assignments, maybe some important assignments that can potentially validate these constraints. So at Intel, we generate a new combinational circuit that somehow represents all these important assignments we want to verify. So by solving the OLSAT problem, we can iterate over all the problems we want to verify at our original circuit.
Thank you.
All right, I think we have to move the other questions to offline because we have a very tight schedule for this session. So let's thank again the speaker.
Okay, so we are through with the technical sessions of the day, and we have a reception waiting for us outside. But before that, I'd like to invite Dr. Sachin Lodha, who's one of the very senior scientists at TCS Research, to speak a few words. I mean, TCS has really rolled out the red carpet for us. So I thought it'll be a good occasion to hear a little bit about what's happening in TCS, particularly things that are relevant to the community.
Yeah, thanks. Thanks, Supratik. Hope I'm audible. So one good news I have for you is that, yeah, so one good news I have is that I don't have any presentation. I'll just speak. So first of all, a very warm welcome on behalf of all my colleagues in TCS and especially TCS Research. So we have been seeing Venki, Ravi, Rishikesh, Abhishek, all this team doing a lot of running around for past several weeks and months. And this was very awaited event for us. As you can see, this facility is new, but TCS Research goes long way back. We moved here only 4 months ago, and this is the first major event we are doing here. And we are very happy that, and very thankful and grateful to the SAT steering committee for giving us this opportunity for hosting first ever SAT in India. So again, thank you for that. So since we got this opportunity, on the podium to speak about TCS and TCS research, so I'll quickly sort of talk about it. So TCS, I don't know how many of you are familiar with. TCS is the largest IT company in India. It is also, by some method, the second topmost brand in IT services in the world. TCS was founded in 1968, and we are now in our 6th decade. So over years, TCS has really perfected the art of, executing the best practice. Okay? So where does TCS research come in here? So TCS research, our motto is to help invent the next best practice. Okay, so that's what we do at TCS. TCS Research was founded in 1981 in Pune. Okay, so this is our largest research center. I don't know you have got opportunity so far to visit our lab, next door. But I'll really welcome all of you to come and spend time with us and see what's happening. So over here, TCS research has grown significantly. We are close to 1,000 researchers spread across, majorly in India and also abroad. We have labs in all major cities in India, just like this. And we work in very diverse areas, okay? So if you think of any standard computing field, like software, or of course, foundations of computing, data sciences, deep learning, we are there. But not just that, outside of computing field, we also work in behavioral and social sciences, physical sciences, life sciences, and so on, right? So we have a lot of breadth and of course, tremendous depth now over the years. See, one unique advantage of TCS is that we work for majority of Fortune 500 companies. And because of that, we are very close to the real problems, right? So one major thing we do as part of our research activity is problem discovery. We talk to a number of customers, our business teams, analysts, and that really helps us identify problems that have a lot of real world relevance. And the problem solving part, while we have incredible talent, we also do it in a very collaborative fashion. So we extensively collaborate with academia all over the world. At any point, we'll have 25 or 30 such very active collaborations with top academic places throughout the world, including India. And so I'll just give you some examples of this, right? That are kind of interesting work happening in TCS research. So for example, we had experts in chemistry, biology, and AI come together to build digital twin of human skin. And that's finding great applications in medical health and also in cosmetics industry. We have had collaboration between material scientists, software engineering researchers, and knowledge engineering teams to build integrated computational material engineering platform. This is a program we launched almost a decade back, and this program is now seeing a lot of traction across different sectors. Of late, our cybersecurity research team is closely working with the program analysis researchers, to attack the very interesting problem that has been posed because of the advances in quantum computing, which is building resilience against quantum. So new post-quantum crypto standards are around, and how to migrate existing applications from classical crypto to post-quantum crypto happens to be a huge challenge across industries. In the past, so this is called as Y2Q problem. In the past era, when there was a Y2K problem, TCS research did a very fascinating work, in automating this kind of transitions, which has really helped TCS leapfrog the competition. So number of such interesting projects and research programs are going on, and I'll really urge all of you to come and visit us in the lab. I'm aware that post this conference, we are organizing 1 week of Research Expo, where I'm hoping that a lot of students will stay back and get opportunity to closely interact with our researchers and learn about these exciting things firsthand. I'm sure you all by now are very familiar with Venki and team and the exciting work they are doing in the foundations of computing. I'm also aware that there's going to be an industry session where you'll probably hear Venki share some of those nuggets. But this team has been working in different domains, including software verification, automotive domain, banking and insurance. There are diverse areas where you will find applications of SAT, and SMT solvers. And this is what this team has been exploring. So looking at, in fact, even this conference, we observe that it's just not TCS, but there is support for a number of different industries, like including Cadence, Synopsys, AMD, Google, Microsoft, Amazon. So one suggestion I thought I'll give from TCS side is that for this conference to think of including an industry track going forward. From TCS point of view, we are observing that there are many areas where you could find applications of SAT and SMT solvers, but probably there is not enough dialogue between the researchers and practitioners. That is probably resulting in not a major application of this. So having an industry track will definitely help you, bring these communities together, and conversations between them will lead to maybe interesting technical advances as well as practical applications. So something I will urge all of you to consider. As I mentioned, TCS work across different sectors and domains, and I have a very good understanding of domains and the context, in which they operate. So it is quite possible that if you want to scale SAT and SMT solvers for industry applications, bringing the context might be a way to sort of make them more scalable, efficient. And there again, I think industry and especially my colleagues in TCS could contribute heavily. So these are suggestions I thought I'll share at this forum. And hopefully, we'll see sort of opportunities for industrial practitioners and researchers to come together and solve more interesting problems. At TCS, so this is something I thought I'll share for students here, that we have been running what's called as a TCS Research Scholarship Program. So every year, about 40 to 50 PhD students in Indian institutes. We sponsor them for their PhD studies. So if you are not aware, I hope this is an opportunity that you might want to take. Also from students' point of view, we offer internships and postdocs throughout the year. So if you really want to understand, what other exciting problems we are working on and get, inputs for your ongoing research, you should explore the possibility of coming and working with us. As I said, we have labs all over India, and you might find a convenient location to work from. I think this is really incredible. I mean, again, thanks Supratik and organizers for giving us this opportunity, to host such a major conference and having you all of you here. I hope you are satisfied with the arrangements, but just in case, I will love to get your feedback so that we can do even better job next time we organize such major events. My congratulations to all those authors who have paper acceptance in this forum. And of course, those whose paper didn't get accepted, I'm sure they had a lot of good feedback to improve their work. And again, I mean, my thanks and appreciation to the STAC committee. And I hope that going forward, we'll see more opportunity for researchers and practitioners to come together and work on interesting problems. With that, I like to sign off, and best wishes to all of you and to the conference. Thank you.
Thank you, Sachin. Yeah. Okay, so I guess we can go and enjoy the reception. And after that, we'll have to come back here in this same room. So there'll be the cultural program. And it is important that we start the program on time, because if we get delayed, there is going to be a fire drill shortly after the concert ends. And if we get caught in the fire drill, then you have to stay here until the fire drill gets over. Okay, so it's important that we start the concert on time, which would be at 6 p.m. We should be back here by 6 p.m. The reception is outside.